Good.
All right, so we'll continue with the second.
Yeah. Thanks everyone for showing up early. And to Dimitri for letting me go first, and an unavoidable meeting in the afternoon. So I'm very proud of myself. Because between yesterday and today, I managed to type up notes for the first two lectures as a PDF file. It probably is riddled with typos, and certainly the referencing is not complete. I haven't acknowledged my grants and none of that, but the science, I think, is, as far as I know, is correct. So,
And it should be uploaded by the end of the day.
oh, it should be uploaded by the end of the day. Perfect. Uh, but, uh, so one advantage of typing things up is that some of the more detailed documents, maybe it's easier for you to scrutinize them in the privacy of your rooms. So I won't go over them on the board and bore you with some details. Okay, so I'm going to pick up where I left off on Monday. So I gave this survey of the landscape of quantum phases and phase transitions, and I said I want to revisit some old topics, possibly from viewpoints that may possibly be unfamiliar to some of you, right? And that was good. I started with trivial insulators in 3 dimensions in the presence of time reversal. Uh, so I'll start where we left off, right? So, and you can read this. This is something that I started talking about on Monday, and we'll just pick up right from here, right? So this much I think everybody agrees with, right? Uh, so what I started talking about towards the end of Monday's lecture was to say that as a legal but impractical probe of this insulator, let's imagine embedding a magnetic monopole into the system and asking how the system responds, right? Now, magnetic monopoles in a quantum mechanical system with charge E electric charges. There's a very famous argument due to Dirac that the strength of the monopole must be quantized in units of H over E. Uh, so I work in units where H bar and E are 1. So H over E will be equal to 2 pi. So this from the magnetic monopole, you can only have the total integrated flux. It can only be multiples, integer multiples of 2 pi. So let's introduce a basic strength monopole, a 2 pi monopole. Imagine it's a Gedanken experiment, embedding it into the medium. And okay, what does the medium do? Right? Now it's a dielectric medium and it can polarize its surroundings. So the monopole may pick up some electric charge. Uh, uh, so then we can ask about the fate of the time reverse monopole, uh, uh, charge QE. So time reversed monopole, we call it TM, also charge QE. So the time reverse monopole has the opposite magnetic charge, but the same electric charge, right? And now what I said was, let's imagine bringing these two together till you get rid of the magnetic charge completely, right? And whatever remains must be an excitation of the system, right? The monopole itself is not an excitation. Just take the Hamiltonian of the system and solve it. You'll never find the monopole. So I'm modifying the Hamiltonian by introducing this as a probe. And then it has some charge. But now I get rid of the magnetic charge and ask what happens. Yeah. Right, because electric charge is even, so electric fields are even, and magnetic fields are odd. Magnetic monopole is the source of magnetic field, right? So if the magnetic fields change direction, the magnetic charge has to change sign.
So like by both magnetic charge and electric charge both?
Right. So this probe monopole has a magnetic charge of 1 in units of 2 pi. And I'm saying, suppose it has some electric charge QE. Then under time reversal, it'll go to a magnetic monopole of strength -1. But since the electric charge is even at a time reversal, the electric charge will stay the same. Right? Yeah.
So the magnetic monopole, when you put, does it have an intrinsic charge QE or is it nucleating a charge QE from the medium?
It's nucleating it from the medium. Yeah.
Am I right? You could have actually do this experiment in principle
With a bar magnet.
with a superconducting tube with a two
Flux quanta.
superconducting flux quanta through it and ends inside your material.
Yeah,
Does it behave like two?
that's right. That's right. Though it would locally break time reversal. Right? But
And over outside of the tube here, if the two even electrons that went around wouldn't feel it.
exactly. That's right. Yeah. So one could do that. That's the Dirac string, if you wish. Right? But conceptually, it's so much nicer to just get rid of all time reversal breaking at the end of the story. Right? But that's not crucial for the argument that I'm going to present, right? At this stage. But eventually, it'll be important to be able to combine these.
Yeah.
And
That's just shrinking.
yeah, you have to shrink your tube, which is probably not a practical thing. Right? Yeah.
It's more practical than putting monopoles.
Right. But once we go down this route, might as well go to the extreme.
Does Dirac quantization depend on the medium gapless or gap?
Oh, Dirac quantization is a very general thing. It's always true. Now, whether you can talk about the local charge or not as a well-defined concept, that depends on whether the medium is gapless or not. Right? So here it's an insulator. I'm assuming it's a gapped insulator. So then you can define the charge associated with the monopole.
Why would the monopole fix the charge? It has magnetic field, not electric field.
Right. So it may not pick a charge, but suppose it picks a charge. Let's see what constraints we can put on how much charge it can pick up. Right? Now, whether it picks it up or not is an energetic question. We just want to understand what's possible. Right? Okay, very good. So let's bring together these two things and get rid of the magnetic charge. Am I the only guy struggling with this? Success. Okay. Now, we can ask about solutions to this equation. And there's two classes of solution. Right? So within each class, you can easily go from 0 to plus E by adding an electron. Right? You have electrons in the system, just add it. Right? And likewise, from E over 2 to minus E over 2 or E over 2 to 3E over 2, just add a number of electrons. Right? But there's no way to go between these two classes. Right? Yeah?
If you have an electron, it's how like going from one band to the other one? Because
there's no band here, right?
yeah, but I mean like the excitation band.
Yeah, so imagine that my local potential is such that it is bound in electron, right? So then you can change the charge. So that can be controlled by the energetics of your Hamiltonian. But there's no way to control the energetics of the Hamiltonian to go from here to here, right? We just don't have available any object with charge E over 2 in the system, right? So, so any given trivial insulator in 3 dimensions falls either in this class or in this class, right? So it's potentially, these arguments tell you there's 2 distinct classes of time reversal protected trivial insulators in 3D, at least 2 distinct classes that are distinguished by this probe. In one, you belong here, in the other, you belong here. Yeah.
You split the half from a one, and when you bring a monopole.
Split the half into the one.
When you have a monopole, you're saying bring a monopole. But what if this QE being half E by 2 is not a full E by 2, like an independent E by 2? Originally some E which got split into E by 2 and I put product factor to the monopole, and some remaining E by 2 still.
In practice, if you do this experiment, if I do this experiment, that's what will happen. It's like someone was asking me, if you throw a monopole from the outside world into the system, that's exactly what will happen. Charge must be conserved, right? So then what will happen is that as it goes into the bulk of a system with this property, the monopole will have a charge half, but how is charge being conserved? It must be that the remaining charge half is living at the surface between the vacuum and this medium, right? But still locally in the bulk, if you look near the monopole, you'll see that it has something that distinguishes it from this other class of insulators. Yeah. No. By definition, we don't have fractionalization here. The monopole is a probe, and this probe has a fractional charge.
Yeah.
There's no fractionally charged excitation in the system.
I see.
Right?
Yeah.
Because I decreed that you don't have fractionally charged excitations. But my probe may pick up a fractional charge. I'm a simple person. I don't do exotic things. At least not for the next 15 minutes. We'll do exotic things later. There are other phases you can talk about, but now I want to talk about trivial phases. There's always time to talk about exotic phases, but let's understand trivial phases first, right? Oh, the medium is an insulator, right? So charge can't flow. Yeah.
I put like a muon in, and the muon has charge -1, but it will get screened, I guess, presumably, and so you could get some total electric charge that this probe would have now. Is that right? And would there be any constraints on this, or can this be any?
So the muon is just an ordinary charged particle, right? And people routinely put muons inside solids. And there's some local electric field, and there's an electric field if it's an insulator. And it's no different from having some charged impurity, right? If you can put some ion and it'll have to be an integer in the sense that it's an insulator, then integrate the charge density over some region, right? You'll get some fixed charge, right? It'll be affected by the dielectric constant. That's right. Yeah.
Dielectric, some random real number, then it would not be an integer. Is that right? If I have a dielectric constant, square root 2.
Yeah. So there'll be some polarization around the medium, but if you integrate, right, over some large but finite region, then with very small, the larger you make the region, the sharper the charge will be defined, right? and it will have to be some fixed integer charge, right? No?
Or
Yeah,
there's polarization charge that appears at the edge, but if you calculate the electric field that's coming out, it's E over epsilon.
that is true. That is true. Yeah.
I think it's if you move it, how much charge.
If you move it, how much charge? No, that's absolutely correct. Yeah. So that's a bit more subtle. Yeah. So sorry, I misspoke. Yeah. Okay. So where do we use time reversal in this argument, right? So we use time reversal in saying that the time reverse monopole has the same charge as the original monopole, right? If I don't have time reversal, these two can have charges that are not related to each other anyway. So then I can't run this argument at all. Okay. And once again, the monopole is a probe. It's not an excitation. So it's allowed to have fractional charge. Yeah. Yeah, so monopoles as point particles only live in 3 dimensions. Okay, I don't know about 26 dimensions, but in 2 dimensions, you can make different kinds of arguments, but let me restrict to 3D. In 2D, monopoles are events in space-time. They're not point particles, right? And 2D, you can do it with pi fluxes, but it's more sophisticated. Yeah, finally, this distinction is a sharp distinction that doesn't care whether I have interactions, whether it's a free fermion problem, whether there's disorder in the system. It's a sharp distinction, right? Because it's the fact that there's quantized to be a half is protected by time reversal. So long as I have time reversal, any Hamiltonian, there's no way to smoothly deform this class into this class, right? So this quantization of the electric charge in a probe monopole guarantees stability to all perturbations that preserve time reversal. Because if you break charge conservation, this entire argument is meaningless, right? So you need both charge conservation and time reversal to protect this distinction. Okay, so I've given you sort of some very general argument, but now let's ask the following question. So this possibility nobody will argue with, right? If you take trivial insulators, this is what will happen. I mean, familiar insulators, this is what you expect to happen, right? The question is, when can this happen, right? Can we say anything about when this possibility, which seems to be allowed by this logic, can actually happen, right? So what kind of system supports QE equals C over 2 charge monopoles? So there's a very simple way of thinking about it, which really goes back to this picture, right? Yeah.
So if I have my insulator Hamiltonian plus magnetic monopole that has a that would give me a charge of plus, and then I have a different insulator Hamiltonian that would give me a charge of plus 2e.
Yeah.
Then is there a way to smoothly continuously deform that one insulator Hamiltonian to the other?
You can without a bulk phase transition by changing, say, the depth of some local potential, right? So you just bind one more electron, right? But in the bulk, there's nothing, right? Just locally, you're changing some. Yeah. So we have the tools to answer this question based on this argument, right? Because if QE is E over 2, then we know how to construct the charge E object, which is the basic charge carrier in the system, right? So the basic charge carrier as Q equals E, and it's a bound state of M and Tm, right? Because M has QE equals a half, and Tm has QE equals equals plus half, and this bound state has no net magnetic charge, and that's how we created. That was the basis for this argument, right? So we can understand this bound state, then we know we can constrain what kind of basic charge carrier we have in the system. So this is a two-particle quantum mechanics problem. That's a small variant of a classic problem in first year of graduate quantum mechanics. Probably, I don't know, at least at my university, we teach graduate quantum mechanics from a book by Sakurai. Probably many people are familiar with the book. And there's a wonderful chapter which many people think is an indulgence, which is on the quantum mechanics of a charged particle moving in the background of a magnetic monopole. I always teach it when I teach that class because I think it's really cool. And you learn all kinds of wonderful things about that problem. How many people have solved that problem before in your life? Some, but not all. Steve Kivelson, very good. Anyway, so that's a homework problem for you. Do it yourself or go to Sakurai, read that appropriate chapter. It's not a chapter, just two pages in Sakurai. It's also described in Jackson. So it's legal stuff, right? It's in all the classic textbooks of our field. And so let me not solve it here. This is almost the same problem, but let me not solve it here, but I'll give you a few sketches of phenomena. Suppose we just treat this classically initially, right? So my monopole is sitting here, and my anti-monopole is sitting, my time reverse monopole is sitting here, and they have some electric charge as well. And let's assume that these are not moving, these are just classical objects. Then there are both electric and magnetic field lines associated with this configuration, and you can calculate the field angular momentum, right? That's why it's in Jackson, horrors of pointing vectors and X cross, E cross B. So you can do that calculation. It's some integral over all of space. And the orbital angular momentum, it turns out when you put in all the units for the monopole has strength H over E and so on. And if this relative vector is R, the orbital angular momentum is H bar over 2 times R. Again, this I'll leave to you as a homework. It's solved in Jackson, essentially the same problem is solved in Jackson. So when you quantize it, this suggests that the bound state will have some internal orbital angular momentum. And indeed, that is true. And it turns out the bound state has half integer angular momentum. But it's an orbital angular momentum, right? Charge moving around a monopole has an orbital angular momentum that's quantized as a half integer, right? So this is classical.
Bound state between an electric charge and a magnetic charge.
That's the Sakurai problem.
Okay.
Here it's a slight variant where you have electric charge half, monopole strength plus H over E, another monopole with strength minus H over E,
okay,
and with charge E over 2, E over 2. But, when you set it up, it's the same problem.
Okay.
Right? With one small difference, which I'll just mention in a minute, and which will be important for us. No, you're right. So this is our hat. Sorry, thank you. It's the angular moment. That's the only direction it can point in, right? Not that. Thank you. You're right. Yeah. Yeah. Right. No, that's not what goes into this calculation. What goes into this calculation is just take the electric field lines the magnetic field lines and do R cross E cross B integrated over all space. It's the orbital momentum in the electromagnetic field configuration. Classically. No, this is independent of the Hamilton. This is in Hamiltonian independent state. Yeah. We'll talk about time reversal in a minute. Yeah. So now quantum mechanically, so in quantum mechanics, so you can take a simple Hamiltonian, p squared over 2m, where p is defined appropriately in the presence of the vector potentials, the monopole vector potentials, and so on. Again, how to do that is how to write down vector potentials for monopoles as described in Sakurai. So I won't bother with that here. So you can show that the ground state has orbital angular momentum of half, right? As anticipated from this classical calculation, right? In fact, all the excited states, every state in the spectrum has half integer orbital angular momentum. Okay, yeah. Sorry? Right. There's a monopole and a charge, right? And we have to reverse the strengths. We'll talk about time reversal, which is closely related in a minute, right? Yeah, time reversal is obviously going to be important because I'm talking about time reversal symmetric systems. So if you wish, this gives you a mechanical way to think about spin. Right? Spin is usually just introduced as some abstract thing. It's generate something that satisfies the angular momentum algebra, blah, blah, blah. But here we have a way of constructing a particle where something is actually spinning around something else, and it's giving you spin. Right? This again beautiful things that Dirac realized in the ancient times. All of these ideas on monopoles are due to Dirac, but it's explained in many places by now. Okay, so let's talk about time reversal, right? Under T, M goes to Tm, right? So I had to flip the orientation of the relative vector R, implies R goes to minus R. Now, again, as this, you might anticipate from this, if you take this R vector, this relative vector, and you project it to the ground state doublet, right? The ground state has internal orbital angular momentum of half, so it's a doublet. So if you project this R vector in the full Hilbert space to the ground state doublet, it has to become some vector that's odd under time reversal, right? For a two-level system, the only vector that's odd under time reversal is the spin vector itself, right? So let me call it J equals the spin half operator. Implies that under T, J goes to minus J, which is the usual transformation for angular momentum, right? And so I think that answers your question. And furthermore, this implies that this doublet is a Kramers doublet, right? Again, first year quantum mechanics, graduate quantum mechanics, right? Kramers theorem follows for spin half states. The only thing that's needed is the action of time reversal, and this is the standard action. Okay? This means that I don't actually need rotational invariance to preserve the two-fold degeneracy. I can break it, and I'll still have this doublet. Okay? Okay, so what we learn implies the bound state is a Cramer's doublet. But remember that this bound state is the basic charge carrier of my system, right? So we conclude that the basic charge carriers must be Cramer's doublets under time reversal if I ever were to get an insulator with this property for probe monopoles. Okay. Now, finally, not finally, but last but one step, the fact that this has internal spin of half suggests that the statistics of this particle will be a fermion, right? Spin statistics theory. And there's an internal spin, right? This protected even if the system doesn't really have rotational symmetry and things of that sort, right? In fact, that can be shown quite explicitly. It was shown by one of your former colleagues, maybe when you were still at Stony Brook, Goldhaber, Alfred Goldhaber in 1982, that this charged monopole bound state is a fermion. Though the two things that you're binding are each bosons, but the bound state is a fermion, right? Again, it has to do with the internal angular momentum. So a lot of peculiarities about this charged monopole system. Starting from Dirac, people discovered it over the last many decades. But we use all those peculiarities. Further, it is a fermion. I have a reference in the notes that I've typed up, the actual journal reference. Yeah. Right, right. So that's the argument. You can do the Sakurai calculation explicitly and do this projection explicitly and check it if you don't just want an argument, right? It's exactly the spin. No, the point is there is a two-level system here. And in this two-level system, in this Hilbert space, what are the operators, right? There's the identity operator and there's three spin operators. Exactly, yeah. Yeah. Hayu and then. Yeah, so for this purpose, that is true. But for this purpose, the rest of the medium is completely inert. There's nothing going on. It's a trivial state. And I have this, I'm just solving this two-particle problem. Right? Of course. The microscopic system is not Lorentz invariant. At low energies, I have nothing. It's a topological phase. It has every possible symmetry. Every possible invariance. It's diffeomorphism invariant, everything, right? So you can just use this logic. Or if you really want to if you don't want to buy that, instead of solving a two-particle, so I've solved I've not solved it. I've sketched the solution of the two-particle problem and set this internal spin of half, solve the two-particle problems, and then actually do an exchange, right? That's a kind of logic that's in Goldhaber's paper, right? It's just doing quantum mechanics, not relativistic quantum mechanics. Yeah.
On the spatial inversion, the angular momentum, but this R vector.
No, so yeah, so you also have to, under spatial inversion, you have to ask about what happens to electric fields? They're odd, right? Magnetic fields are even under spatial inversion, right? So the magnetic charge doesn't actually flip under spatial inversion. So it's a bit more delicate. Yeah, so you had a question? Right, so the Goldhaber paper does the explicit exchange, but it's reasonable, given that there's internal spin of half, right? But if you're worried about it, read Goldhaber's paper. Yeah.
whether we're taking T with M, magnetic charge to minus magnetic charge, or if we're picking it to send R to minus R. I feel like those are equivalent things, but when you do both, nothing happens.
No, I'm not doing both. This implies this. Right? Because, well, if I look at that configuration, if I flip M and TM, R has to go to minus R.
So R here, quantum mechanical problem. What operators exactly?
So you'll set it up as one localized TM moving in the background of an M, right? And then there'll be coordinates for TM and M. There's an R1 and R2. So R2 minus R1 will be R. And then you solve the problem. You find this ground state, and then you take this in this big Hilbert space, inject it to the ground state doublet, ask what operator it becomes. There are only 4 operators for a 2-level Hilbert space. It's got to become 3 of those, and it can't be the identity. Yeah. Yeah, where the monopoles don't need to have intrinsic spin. Yeah. Yeah.
Is inversion why is
T is time reversal. Projection. P is a projection to the ground state doublet. Yeah.
So this angular momentum, you said it's in the electromagnetic field, or is it also involves actual rotation of dumbbell?
No. So the classical calculation is a calculation of the field angular momentum. And then the quantum calculation just solves the quantum mechanics problem, right? Doesn't regard just solves the quantum mechanics problem. And you can think of this as a Berry phase effect, right? So when a charge moves around, it depends. The classic Sakurai problem is fixed monopole charge moves around, it picks up a Berry phase. That's 1/2 the solid angle. Here, if you repeat that Berry phase calculation, you'll see there's 2 factors of 1/2 and 1 factor of 2. So you again get 1/2 of the solid angle. And that then forces the rest of the conclusions. Anyway, I'm giving you more detail on how to solve the 2-particle problem, but
You're saying there's a connection. So in the quantum problem, Berry phase is what gives the spin 1/2.
yeah, you can think of it that way. Yeah.
You're saying that's also the classical angular momentum of electromagnetic field?
No, the classical angular momentum is just meant to motivate, right?
Because I don't see a connection.
Yeah. So if you read Jackson or something, there is a discussion of, is this a coincidence? Is this the same reason? And yeah, so I'm not going to. The real thing to do is the quantum calculation, right? But wet your feet by doing the classical calculation, right? Yeah. Okay, so I'm almost there. If I can find my notes. Yeah. What have we learned, right? We've learned that the basic charge carriers must be fermions, which are Cramer's doublet under time reversal. If you have a system of bosons that form a trivial insulator in 3D, you cannot have this option. Okay? Or if you have Cramer's singlet fermions, spinless fermions, can they form a medium in which this happens? That's also not possible. Okay? Now, I think some of you said you were field theoretically inclined. You might recognize that this is the same as what in field theory connects to the usual description of the topological insulator in terms of theta equals 0 or theta equals pi, this axion angle. And this F wedge F term in the electromagnetic response. Actually, Peter is sitting somewhere. Peter did an experiment looking for this theta equals pi 10 plus years back, right? Around that time, right? And then there's something called, I'm not going to explain this, so I won't take questions now. I'm happy to talk afterwards. This statement can be understood as what's called the Witten effect when you have a theta angle. And people have done in topological insulator, pre-fermion topological insulators, calculations, explicit calculations demonstrating this Witten effect. And the usual argument that's made in field theory is to say that theta equals pi is time reversal symmetric because theta is periodic mod 2 pi. Now, we've learned from doing all this that that statement can only be true for Cramer's doublet fermions. Now, the serious field theorists know that it's theta is periodic mod 4 pi for bosons and mod 2 pi for fermions, right? So that is can be reconciled with the standard story easily. But the difference between Cramer's doublet fermions and Cramer's singlet fermions is very subtle in field theory. It turns out that for Cramer's singlet fermions, theta is not periodic mod 2 pi. And just based on E dot B and things like that, it's a bit hard to understand. And the real experts understand it. It turns out to really distinguish between Cramer's doublet and Cramer's singlet fermions. They had to put this theory with this theta term in a non-orientable manifold and figure out how to introduce U1 gauge fields in that manifold. And there's two different ways in which you can introduce it. And that imposes constraints on the periodicity. So it's very, very subtle and complicated. The experts understand it. But here, I think you just solve this two-particle quantum mechanics problem and you understand. So I think there's value to thinking about it this way. Wasn't going to allow questions, but just on this last topic.
It's a question about the two-particle problem.
Yeah, good.
So just like, I mean, in quantum mechanics class, you're told that half integer orbital angular momentum isn't allowed because of this. You need the wave function to be single valued.
Yeah, very good.
I mean,
so
what's going on?
Yeah, so again, for a monopole, for a charge moving in a monopole background, the wave function is has to be defined very carefully because you have to choose a vector potential, and there's no global way to choose the vector potential. You can only choose it in patches, and then to stitch the patches together in some way. So all of that, so if you do that carefully, there's no inconsistency. Right? It's because of the presence of this non-trivial vector potential, which can only be defined locally but not globally, that is allowed. Yeah, very good point. Okay, so yeah. Yeah, so the composite object is a fermion. That's right, yeah. The single one is a boson. Two bosons bind together and form a fermion.
Why is this?
It could be a boson, if I assume that the initial monopole is a boson. Yeah, that's a great question. And the answer is it depends. Right? But in either case, bound state of two fermions also can't be a fermion, usually. Right? I can tell you in detail what it depends on, but it's safe, it's certainly possible for it to be a boson, right? Can be a fermion in some special situations. It depends on whether the basic electric charge is a boson or a fermion. The basic electric charge is a fermion, the monopole can't be a fermion unless you're living at the boundary of a 4+1 dimensional universe. That's maybe more detail than you need to know. Yeah. No, I didn't show you. I didn't show you. No, in the QE being half integer case, the bound state of M and Tm, which is the basic charge carrier of my underlying system, that basic charge carrier is a Cramer's doublet. Yeah, so that's the only state. No, in the zero case, I can't say anything. The monopole, then it's just the statistics of the monopole, right? Yeah. No, I don't understand. No, I didn't understand the question. So, maybe let someone else ask the question and then you can articulate what you want to say. Yeah.
I just think of the box state as a single electron.
Yeah, it is the single electron because that's the basic charge carrier in the system, right? Are you ready? Or maybe we go to the next. Yeah.
There, like, what the muon and Senthil both are directly
Sure, that would be true. Yeah. In this top class. Exactly, yeah. Yeah, so for this purpose, it doesn't matter, but strictly speaking, the correct thing to do is to think about a bosonic monopole, and that will bind to some charge. It becomes, as somebody was mentioning, the technical word is it's a dion, and this dion will be a boson, right? This other dion will also be a boson, but their bound state is a Fermi. And that non-triviality comes from the magic of particles interacting with monopoles. Right, let's imagine there's some attraction between M and Tm. Right, again, that's Hamiltonian, right? I allow myself to turn on any Hamiltonian I want in the Hilbert space. Right? Right. Oh, I changed my Hamiltonian to have a short range attractive interaction that comes upon that. No, I proved to you that I proved, meaning I sketched the logic that leads you to conclude that it can only be. Initially, I didn't say anything about what the charge carriers are, right? But I'm saying if this happens, then the charge carriers must be fermions. They must be Kramer's doublets. And oh, then it can be anything. Yeah, absolutely. Yeah. Yeah. Sorry? No, it's in 3 dimensions. So what does mutual statistics mean? Yeah. There's no bulk phase transition, right? Same question somebody is asking. If I change the local Hamiltonian, I can induce another bound state locally without changing anything about the bulk properties, right? Yeah.
Does the argument change if you were to do the same thing in 2D?
I'll talk to you separately. Another homework problem. I have all these as homework problems. I just didn't put them up. I didn't want to drag the audience too far into this topic by overwhelming you with too many homework problems. Yeah. Oh, yeah. So all that is taken into account when I wrote that. Yeah. If you change the strength of the monopole or the strength of the electric charge, you can change the angular momentum. Yeah. All right. I want to make one last comment about this before moving on. Yeah.
I mean, this argument is very general, so it does not really depend on how big the third dimension is. So it could be that it's still 3 dimensions, but very, very thin.
Oh.
It would still apply.
I want to think about the thermodynamic limit.
But it's not necessary.
Everything else is left as a homework problem for the audience. Allow me to take the thermodynamic limit, be in the ground state, change the Hamiltonian in any way I want, so long as it's a legal Hamiltonian. Any of you who wants to do anything else, feel free to do it. This is all I'm going to do. Right? So the final comment I want to make, I'm not even going to write it down. You can ask whether, so we'll just call these charge carriers ordinary electrons. Right? They are fermions, they are Kramer's doublets, let's call them electrons. Can these electrons have a conserved ordinary spin? Forget about this internal thing that came up. Can they have a conserved SU2 spin the usual spin half of the electron, right? And the answer is no, because S squared is time reversal invariant, and both the monopole and Tm must therefore have the same S squared, right? And S squared for SU2 can only be half, 1, 3 halves, blah, 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 right? So if both of these have the same S squared, their bound state can never have spin half, right? Never have S squared equals 3/4, right? This means that all this phenomenon cannot happen in an electronic insulator where spin is a good quantum number. But time reversal needs to be preserved, which means that it must be spin orbit coupled, right? So we see the importance of spin orbit coupling for producing a non-trivial time reversal protected insulator. Okay? There's a lot more that we can say from this point of view. One can sort of recover all of topological insulator theory and much more from this point of view, but I'm going to stop here, right? And make maybe just one comment, which will set me up for the next topic, which I already described. Just give me a second. So this non-triviality of the monopole implies that the surface, an interface between an insulator with this property and an insulator with this property, which can be the vacuum, that surface cannot be trivial, right? Because if I start from the trivial vacuum where this is true, and I throw my monopole into the medium, the half charge has to come from somewhere. It has to come. The only place where it can potentially come is when the monopole passes through the surface, right? So the surface must have alive degrees of freedom that enable a 2 pi flux going through it to suck in electric charge of a half, right? So this kind of phenomenon where a 2 pi flux going through a 2D system, my surface is a 2D system, where it sucks in a charge of half, sucks in some charge, is familiar from the quantum Hall effect. So it's almost as though the surface must have a Hall response that's half mod 1, right? And that we know is a standard property of the surface of a topological insulator. And there's many other things you can say, but that's going to be the end of the story. Except for one comment. The surface state of this kind of insulator realizes symmetry in an unusual manner. People say it has an anomaly. What it means is that if you couple, in this context, if you couple a probe electromagnetic gauge field, that the surface theory alone is not time reversal invariant, but the combination of surface and bulk is time reversal invariant. The entire system is time reversal invariant. If you just look at the surface, it looks as though it has a non-zero Hall conductivity, that it's able to suck in charge when flux passes through it, right? But of course, the full system preserves time reversal. So the surface, regarded as a standalone two-dimensional theory, realizes the symmetry in an anomalous manner. That's one way to talk about the anomaly. Okay? So let me make a connection to the posters. Not your posters, but Pam's poster. So this means that the surface is dancing to the tune of one higher dimension. That's one of the posters there. Yeah.
Could you walk through the argument again about why this thing can't be the electron can't be an S squared?
Right, because if the electron is spin half.
Yeah.
Now, what about this S for the monopole, right? Whatever S the monopole has, Tm must have the same S. Now, you can't combine two spins of the same S and get a spin half object.
Yeah, okay. But, okay, yeah, I think.
Yeah, can I follow up? So, you said that S can't be a good quantum number of our original Hamiltonian.
Right.
For that reason. But M isn't an extension of the original Hamiltonian anyway. So why did M, the fact that M doesn't have a good S quantum number doesn't mean that.
Right, so I probed my system with the magnetic monopole. The modified Hamiltonian, which includes this probe, is still spin rotation symmetric. If spin rotation were a symmetry of the Hamiltonian, I can label the states of this Hamiltonian with the S quantum number. And then I introduce a Tm, and I get rid of M and Tm.
Well, is it obvious why introducing M does not break S?
Right. So I introduce M just by turning on a vector potential, right? The monopole vector potential, right? Again, you can do this very explicitly for the free Fermi model of a topological insulator, right? Yeah.
So having a TI to rely on no spin orbit and conservation of spin angular momentum is not generic. Having extra symmetry cannot, can only make it more, SPT then, or more of
No.
the original Xu chain was not putting in spin orbit. It's just different classification. You get Z instead of Z.
Yeah. So if you have right. So in 3 dimensions, if you have SU2 symmetric electrons that spin half, you don't get a topological insulator within band theory either. And that's consistent with this more general consideration, which is true beyond band theory. So the classification does change. If you impose higher symmetry, you can trivialize formally non-trivial phases.
Less trivializes.
Yeah, not necessarily. You can find paths. It's a question of whether you can find a path within the space symmetric Hamiltonians. If you have higher symmetry, maybe there's some other path. Right? No. Yeah, not for topological insulators. For topological superconductors, that's true, but that's a different problem. Yeah.
Because monopole only couples the charge degree, but not the spin degree.
Absolutely. There's a vector potential that we are turning on. We're not turning on a Zeeman magnetic field or anything. Yeah. Then what does that mean? It's a Kramer's doublet. I specify the symmetry, the transformation of this particle under the microscopic symmetries. And then everything else is mechanism question I don't want to answer. No, if I apply this to an ordinary electronic system, I must have spin-orbit coupling to get rid of the spin as a good quantum number, right? But it can't be some other kind of spin symmetry baking, because that will destroy, I want to preserve the Kramer's nature, right? Yeah, so let me stop this discussion here. The way I'm going, I'm not going to talk about all the things in my notes. So let me make a decision. My initial plan was to talk about these topological insulators first, and then talk about the fractional quantum Hall effect, then talk about Fermi liquids. I think I'm going to skip talking about the fractional quantum Hall effect. What I had to say was very short anyway. Let me skip talking about it. Let me jump to Fermi liquids. And it's actually a good place to jump to Fermi liquids directly without going through fractional quantum Hall. Because some of these things that we are talking about will impact the discussion of Fermi liquids, right? At least my discussion of Fermi liquids. And so this again emphasizes the close connection between completely different topics, right? And though I'm not going to explain it, again, I can explain it outside of the lecture. The same kind of discussion, if you do it for a hypothetical system where electric charge is odd under time reversal and magnetic charge is even, and you more or less repeat the same kind of discussion, then you'll find that if you have 2 monopoles of the same strength, they'll have opposite electric charges, and that object is a Kramer's doublet. Okay? And that picture of this hypothetical system in 3 dimensions, it turns out, is the essential physics to understand the half-fill Landau level in the presence of particle-hole symmetry in 2 dimensions. And there's a one-to-one correspondence between this picture modified to this hypothetical system and the composite fermion of the half-filled envelope. So once again, there's this very close connection between all these different kinds of seemingly distinct phenomena. All right, let me talk about Fermi liquids. So I'm going to focus on some very, very general properties of Fermi liquids that follow just from their symmetries, right? I'll specify the microscopic symmetries of the system. I'll specify the symmetries of the low energy theory of a Fermi liquid. And we'll see that there's a great deal of universal physics that one can extract about the Fermi liquid without knowing anything else, just from symmetry considerations. Okay? We can't extract everything. There are many properties for which we need to know the Fermi velocity, the shape of the Fermi surface. But there are many other properties which follow on very general grounds without knowing anything other than what the symmetries are, right? And that's what I want to talk about. And there'll be a close connection to this discussion of topological phase of matter. Okay. So let me make a couple of comments about global symmetry in many body physics. So usually in condensed matter, we have a microscopic system. So I'll call this the UV system, which will have some symmetry. That's a group, symmetry group, which I'll call GUV. And then the system will settle into, depending on the Hamiltonian, will settle into some phase of matter at low temperatures. So then there's a low energy theory. I'll call this the IR theory. And this will have some symmetry group, GIR. And there's a flow from the microscopic system to the low energy theory. And likewise, there'll be this GUV will map on to GIR in some way. So I'm going to be interested in situations in which none of the symmetries are broken in the ground state, right? No symmetry breaking, right? And so then this GUV has to embed into the symmetry group of the IR theory, right? Mathematicians will say it's a homomorphism, but I barely know what that word means. I just use it. Now, DAR may be bigger than GUV. So this what happens when we have emergent symmetries. The low energy theory has more symmetry than the original microscopic system. Now, for our purposes, the thing that's important to focus on is that not only can GAR be bigger than GUV, but GAR, it's an emergent symmetry. It may itself have this property of having an anomaly. Okay, like we just saw for this, like I just mentioned for the surface of the topological insulator. So why are these anomalies interesting? Right? They're interesting because if we can identify the anomaly, they provide us with non-perturbative constraints on what the low energy system can do. Right? And you can sort of see that already from this discussion of TI surfaces. Right? So long as your bulk is a TI, the surface has to have some properties that are determined by statements about the bulk. Right? Whatever your surface is doing, it can undergo phase transitions, it can turn on strong interactions. Some basic properties of the surface are dancing to the tune of the higher dimension. And so long as you don't have a phase transition in the higher dimension, the surface is strongly constrained to have some physics, right? So if you can identify an anomaly, you have strong constraints on the physics. Okay, and it often happens in condensed matter physics that the symmetry group of the low energy theory has an anomaly, right? In which case, there's a point of view where we can usefully view the IR theory as sitting at the boundary of some hypothetical medium with this symmetry extended into the bulk. And that's a very, very powerful point of view that enables us to make all kinds of statements about the low energy theory that we don't otherwise have access to. And I want to do that for Fermi liquid theory. Right? The most familiar many body ground state, but also one of the most subtle. So other examples where you might have seen anomalies are the chiral anomaly of, say, a Weil semi-metal. Or Weil or Dirac semi-metals, or 1D Masters Dirac fermions, right? Several of you probably encountered this. People have even claimed to have done experiments measuring the chiral anomaly of a 3D Weil semi-metal. Yeah, so these are very general statements. Let me specialize to the system of interest, which is fermions moving on a lattice with charge conservation and translation symmetries, right? So my UV theory is fermions on a lattice at filling nu. Nu is something that I can tune continuously in the metallic state. And let's, for simplicity, take D equals 2 space dimensions. Yeah?
When you still hearing the word anomaly, think about this Fukuyama argument where the measure changes.
Or that is correct.
Is it related at all, or is either just the same word?
It is related, but that's a very formal way of thinking about it. By now, we have very physical ways in terms of surface of SPTs and things like that. We have a much more physical way of understanding all those old things. Right? That's a very mathematical way of stating it. Right? So the symmetries, so I have a lattice, and I have fermions at some filling. So the UV symmetry is charge conservation times lattice translation. Right? So that's the system I'm interested in. It's a system we're all interested in. And let me assume that the ground state is a Fermi liquid. So IR theory is nothing bizarre. It's a Landau Fermi liquid. And so this is Ky and this is Kx. It's a Fermi surface. Need not be a circle, but it's topologically a circle. Assume there's only one sheet to the Fermi surface. And there are well-defined quasi-particles. There's the Fermi C. And the boundary is this Fermi surface. And there are well-defined quasi-particles at this Fermi surface. We'll turn off the pairing instabilities. Right? We want to talk about the Fermi liquid ground state. So it's only the standard Landau Hamiltonian with forward scattering interactions, and that's it. So what is the symmetry of the low energy theory of a Fermi liquid? Right? So that's the question I want to focus on. And I want to ask if that low energy theory has an anomaly, and if so, what its consequences are. Right? So there's a colloquial statement that is implicit in Landau Fermi liquid theory, that the quasi-particle number is conserved at each point of the Fermi surface, which suggests a huge symmetry at low energies. Right? So we should be more precise than just noting that the quasi-particle number is conserved. What we should really define is the number of quasi-particles in some infinitesimal segment of the Fermi surface. Right? It's some continuous object, and it's better to talk about quasi-particle density per unit segment length rather than the quasi-particle number. right? For each point theta, so let me parameterize this closed loop by a periodic variable theta. Yeah.
Right. Even if they're irrelevant, I would still have scattering. How do I think about this as a conserved quantity?
Right. So in the low energy Fermi liquid theory, that scattering is gone. Yeah, they're irrelevant perturbations. The scattering is gone, right? Just the Landau Hamiltonian, right? There's only forward scattering, right? Yeah. Right. So the Landau Hamiltonian does not. The Hamiltonian itself has conservation of every momentum, but it's not applicable to the original electron system unless you're right at the Fermi surface. Right? After all, we know there's a scattering rate that goes like E minus EF squared. Right? Yeah. Right.
In this Fermi surface discussion fall to the symmetry such that GIR is bigger than T.
Right. So, yeah, as we'll see, there's infinite number of conserved quantities in the low energy theory. But in the microscopic theory, there's only charge conservation. Right? So it's huge number of emergent symmetries in the low energy theory of a Fermi liquid. Yeah. But it can also be more discrete symmetries. Right? Yeah. Epsilon k minus mu delta nk plus fk k prime delta nk delta Landau energy functional. Let me. I was wondering if somebody would object. So there you go. All right. For each point theta, there exists a conserved n theta such that n theta d theta equals number of quasi-particles between theta and theta plus d theta. Okay. So now we can discuss what the symmetry is. These are generators of a continuous symmetry. The conserved quantity, exponentiate them and get the symmetries. So the general symmetry element, general IR symmetry element is e to the I times integral d theta f of theta and theta, where f of theta is some smooth function, say any smooth function of theta that's periodic when theta goes around its loop, right? So this defines a huge symmetry group. 1 minute, yeah. And it has a name. It's called the loop group of the group U1. It's a group of maps from a circle to U1. Yeah. Yeah, you can worry about non-smooth choices for f of theta. For my purposes, it'll be enough to restrict to smooth. We'll see why. In a couple of minutes, it'll become clear that it's enough to talk about smooth. Non-smooth, entire can of worms, but we will not need to discuss non-smooth. Yes.
Symmetry at every theta. Is that right?
It's better to think about it the way I've phrased it. Yeah.
And it's really, you could also write it just for every theta, there's a special.
Right. It's more precise to write it the way I've written it. For arbitrary functions f of theta, you can make the f of theta very sharply peaked.
It's kind of like
I don't want to use those words. I don't want to say more than I need to say. Right? I learned this from Steve. The less you say, the better it is. No. Because the only symmetry I'm assuming is U1 in lattice translation. Right? I'm not even assuming rotational symmetry. Right? Okay. Fermi surface is single valued? Yeah, I'm assuming that. Yeah, no. all that you want to do homework for you. Okay, so we want to know how this works, right? How are we going to, how are the UV symmetries embedded into the IR symmetries? So how does charge U1 act? How does discrete lattice translations act in the low energy theory? So the total charge, so GUV to GIR, what does that map, right? So the total charge is very easy. The total charge in the low energy theory is just the integral of n theta, right? The total charge of all the quasi-particles. Now, translations is also very easy. Sorry? Oh, it is fixed, right? Because it's not like you can have some regions of the Fermi surface have charge 2 or something. So translations, when you have a discrete translation by one lattice spacing in the x direction, it changes the phase of all the quasi-particles at the Fermi surface by an amount that depends on their Fermi momentum. Okay? So this then tells us how translations act. So T alpha, so discrete unit translations along alpha equals x comma y. You can translate in either the x or y direction, yeah. No, n theta is like a density. N theta d theta is defined on a small sliver.
Okay, n theta is the local density of the surface. So why is this the total charge?
So n theta is the density of quasi-particles per unit segment length. No, it's just defined on the Fermi surface.
You need to say something else, right?
No, this will be the charge, right? I'm not assuming spatial variation, right? N theta is spatially, it's a total. So if I distort the Fermi surface, right, make it, I have a Fermi surface like this in the ground state, and I do something like that. That may change the charge if the total area changes, and I can get that by integrating n theta.
There's a shift of the charge, which is the charge of the full Fermi sea.
I'm removing the ground state charge. Yeah. Yeah. So the tilde is there because I'm subtracting off an infinite constant, which is the charge of the ground state, right? So how the charge embeds in the low energy theory, I only have to specify the charge relative to the charge of the ground state. Thank you. Yeah. Okay, so T alpha is e to the minus I integral d theta kf of theta and theta times A alpha. A alpha is the lattice spacing. So we see that both the global U1 and discrete translations embed into the low energy symmetry as elements of the symmetry group that I wrote down. Right? There are particular functions f of theta. For the charge, it's just a function that's independent of theta. For the translation, that function is just the Fermi momentum, the alpha component of the Fermi momentum. Okay? Now, the cool thing is that this low energy symmetry group has an anomaly, which will then lead to all kinds of consequences. So let me describe the anomaly. Right? So the IR symmetry has an anomaly. So what does it mean for it to have an anomaly? Right? So I think going back to the discussion of TI surfaces, I said in the TI surface, I said that the microscopic symmetry is a U1 and time reversal. And if you couple the system to a U1 gauge field, electromagnetic vector potential, then the surface alone is not time reversal symmetric. And you have to combine it with the bulk to make the system time reversal symmetric. So the more general statement is that any symmetry that has an anomaly, if you try to couple it to gauge fields, the symmetry is not present. But there is a way, if you can extend it to the gauge field to higher dimensions, then maybe you can make it gauge invariant. Okay. So this may be familiar to those of you who are familiar with the chiral anomaly in for 1D massless fermions or 3D Dirac or Weil semimetals. Right? It's the same story. So here we have a Fermi surface. Now imagine turning on an electric field. The entire Fermi surface will shift in the direction of the electric field. This means that you're depleting quasi-particles from one side and putting them on the other side. So clearly you're not conserving the number of quasi-particles at each point of the Fermi surface. Right? So clearly there is an anomaly once you turn on an electromagnetic field in the system. Now it's more entertaining in this two-dimensional case to turn on a magnetic field. Okay, so let's turn on a B field. So I have my Fermi surface, and I have a quasi-particle. The Lorentz force on the quasi-particle. So semi-classically, we know what happens. The particle moves around on the Fermi surface, right? And it does this, which means that the number of quasi-particles at any given point is not conserved. As a function of time, you're removing quasi-particles from one point and depositing them at various other points, right? Okay.
You then said like Newton's equation. That's an anomaly. It just seems like even like swing anomalies, like
yeah,
that's the force.
No, there's lots of things you can understand through other ways. The power of incorporating these statements into the framework of anomaly is that it streamlines the process. So it streamlines your thinking, right? And I'll soon make a couple of statements before I end, right? Where you'll see how it really helps, right? Let me make those statements. And
when you dissect it, it's kind of mundane, right?
Wait and see. You'll see that it's not that mundane. 10 minutes? All right, very good. I might even be able to finish. Okay, so the first statement I want to make. So this, of course, all of us learn in solid state 101, right? So Fermi surface, you turn on a field, quasi-particles move this way. I want you to view the same picture slightly differently, right? In this magnetic field, this particle is moving around this way, but it won't move around in the opposite way, right? So it's a chiral mode, right? Chiral one-way mode, which you all know from the integer quantum Hall edge state, right? In the integer quantum Hall edge state, you have a bulk that is rigid, has no life, more or less. But at the edge, you have a chiral one-way edge mode. So maybe you can think of this. The interior of the Fermi sea is dead. Nothing can happen. But at the edge, there's a chiral one-way mode. So maybe we can think about the interior of the Fermi sea as being an integer quantum Hall state in momentum space, and think of the Fermi surface as the k-space edge of the rigid Fermi sea. And then when I turn on a physical external magnetic field, perhaps it is true that this integer quantum Hall turns on in the bulk of the Fermi sea, and that's why I get this one-way edge mode. Now that sounds like fantasy, but in fact, it's exactly true. Right? And we can prove this by looking at all these symmetries and everything. Yeah.
What about non-locality in momentum? I mean, it's not quite like a dimension.
That's right. That's right. So you can have Landau interactions that couple these 2 points. But for these purposes, it turns out it doesn't matter. In the sense that, so the emergent symmetry and its anomaly in this Fermi liquid, just like in some systems, when you have long-range Coulomb interaction, in a real topological instead of long-range Coulomb interaction, it doesn't really affect these general topological statements. Right? So likewise here, this non-locality doesn't seem to affect it. If you have scattering, it's a different story. That destroys the symmetry. But this, forward scattering doesn't do anything. Right? So quantum mechanically, just a minute. So this was semi-classical, but quantum mechanically, we can think of the rigid Fermi C in a B field as an IQH state in K states, and the quasi-particle at the Fermi surface as the corresponding edge state. Yeah. No. So this is in momentum space. So it's a bit, you have to change your thinking, right? Yeah. No. But there's a Fermi surface, right? Yeah. Yeah, but I'll come to that in a minute if I can get to it. Yeah. Yeah. Yeah, no, that's a very good question. You can ask whether you can have integer quantum Hall effects with multiple edge states, right? Now, if you only have spinless fermions, we don't know how to do it. It's something I'm working on for the last many years, but I haven't been able to construct it, right? Yeah. Yeah. Yeah.
So there's some dynamical.
Right. So the speed of this edge mode depends on the Fermi velocity. The Lorentz force depends on the Fermi velocity. The existence of the edge mode is a universal property. What symmetry? Oh, there may be other structures associated with this chiral edge mode, which I'm going to talk about in a minute. But that's a separate statement. Somebody had a question here? No? All right. So now let me. So I'm not going to demonstrate this for you, but we did demonstrate that in a paper with Dominic Els. Yeah. The Hall connectivity is 1.
So if I don't have any quasi-particle dissipation from liquid, then I don't have anything on the edge to move into.
No, so if you wish, the entire Fermi C is moving, right? So there is an edge current, right? So from this picture, as several people are asking, maybe if I write the next thing, some of those questions, the answers to some of those questions will be clear. So there's a lot that we know about integer quantum Hall edge states, right? In particular, for this chiral fermion, the integer quantum Hall edge, so it's a one-way moving fermion, right? There's something quantum mechanically, there's something very interesting about this fermion. It is that its density operators do not commute with each other. Okay, so that's yeah. I don't know how familiar you are with that story, but let me state it anyway. So this is the physics of the anomaly, right? The formal manifestation is the following. Turn on 2 pi magnetic flux. So I said turn on a magnetic field. Now let's imagine that the physical magnetic flux in real space is 2 pi. So then in the whole system, that's right. Very tiny magnetic field. So then theta, from this picture as the edge of this momentum space integer quantum Hall effect, one learns, based on what we know about the integer quantum Hall edge, that the N theta doesn't commute with itself. Rather, it obeys a very weird commutation relation where the commutator looks like this. So if you've not seen this, I strongly encourage you to take a 1D chiral fermion, the edge mode of the nu equals 1 integer quantum Hall state, write the expression for the densities, and check for yourself that this is how the density. Normally densities at different points in space will commute, but at the edge of the integer quantum Hall state, they don't commute. And that, in fact, is crucially tied with how this edge state can only live at the boundary of the integer quantum Hall state. That's a manifestation of the chiral anomaly of the edge of the integer quantum Hall state. 2 minutes? Yeah. Yeah. No, it's in real space. This is an ordinary magnetic. So I'll say that this is familiar. If it's not, another homework problem. Okay, so since these things don't commute, so this is how this big symmetry is, you can think of this as why the big symmetry is destroyed. Okay, and this will incorporate all of the questions Nandu was asking about. Okay, so let me finish this discussion. It's highfalutin stuff, right? For what really is very simple physics. But let me derive some consequences of this. Right? It turns out this has a large number of consequences, and many universal properties of Fermi liquids are just determined from understanding this, but not all universal properties. There are dynamical universal properties, and there are other universal properties that I call kinematic universal properties that only depend on these general structures.
So, for ordinary chiral edge, you just bosonize and you have this kind of relation.
Right.
What is the ingredients to do it here from like first principles? Do I need to do it just at the level of the semi-classical equations of motion? Or?
Right. So there is a derivation of this from first principles that doesn't talk about anomalies or anything. That in fact goes back to Eduardo Fradkin from at least 25 years ago. And it was re-derived by Damson from some other perspective, but we now understand that it just follows from the anomaly.
But does it?
So there are microscopic derivations in the literature.
But microscopic at the level of the semi-classical equation of motion for momentum and position, for momentum?
Yeah, so the way Eduardo was originally thinking about it was in terms of 2D bosonization of the Fermi surface with Castaneto in a magnetic field. Subsequent paper with Daniel Bacci.
Magnetic field, you are in the semi-classical picture because magnetic field is so weak. There's no
that's right. That's right. Yeah, you want to work with a very, very weak magnetic field. Yeah. Yeah. Right, but this IR theory, if I turn on interactions and so on, so one of the beauties of the anomaly is that it's a topological property of how symmetry is realized in the low energy theory. You can deform the system within the same phase, and all kinds of other things can change, but the emergent symmetry and anomaly will not change. So there are topological aspects that capture some of the physics of a gapless system. That's why there's a connection between study of topological phases and study of gapless phases. Should I finish or can I take 2 minutes and complete the next story? All right, very good. That's a good deal. I just want to do this for Leo's sake. You know, why are you doing all these fancy things about what everyone knows from childhood, right? As I said, it's a way to understand which properties of the Fermi liquid are kinematic and which properties are dynamical. So let me apply this understanding to derive for you something that you all have probably heard of. It's called Ledinger's theorem, right? I'll show that Ledinger's theorem just follows from these. So Ledinger's theorem is the statement that the size of the Fermi surface is fixed by the density in some universal manner, right? Just like in free particle theory, right? And it was proven to all orders of perturbation theory by Ledinger in the 1960s. And in 2000, there was a nice topological argument given for Ledinger's theorem by Yoshikawa, who put the Fermi liquid on a torus and threaded magnetic flux through one cycle and calculated the momentum transferred in two different ways. So now we'll really see that this is Ledinger's theorem is one consequence of this much more fundamental structure of the emergent symmetry and the anomaly of the Fermi liquid. Okay, so we're almost there. So Ledinger from the anomaly. So we have turned on 2 pi magnetic flux. So let's restrict to turn on 2 pi real space uniform magnetic flux. Then we want to do two things. Now, once I have a magnetic field in real space, we know that the action of translation gets modified, right? A single electron now picks up a phase when you translate it, right? So translation symmetry becomes magnetic translations, right? So we want to calculate how translations act in the original UV theory. We want to know, given this understanding of how translations act in the IR theory, we want to calculate the same action of translations. We want to compare the two. Okay. So in the UV theory, Tx and Ty do not commute. And with uniform flux, the symmetry algebra is that it's determined by the lattice filling fraction, right? One way to think about it is that each electron picks up a phase equal to B divided by the area of the unit cell. You have n electrons. So the full many-body wave function picks up a phase, which is e to the 2 pi I times the filling fraction, right? So this is a very robust statement. By 1 unit, that's right. Unit lattice translations. Now in the IR theory, in the presence of the same 2 pi flux, we know, so T alpha is that equation, the T minus I A alpha integral d theta AF alpha and theta. But we also know that in theta and theta prime is this equation. Okay. So the commutator of two n thetas is not 0, but it's the identity operator. Then we want to calculate this object with this for Tx and Ty defined like this. You know, you can use Baker, Campbell, Hausdorff, you know, that formula, homework problem. And what you find is that Tx, Ty, Tx inverse, Ty inverse is e to the I times the volume of the Fermi surface times Ax, Ay by 2 pi. Okay? So this doesn't know about the lattice filling. It only knows about how translations act and this anomaly story. This knows about the lattice filling. But this low energy theory knows about the Fermi momentum. So some geometry of the Fermi surface enters. Now you compare these two, right?
So can you say the units of VF times area?
VF is the volume of the Fermi surface. Yeah, area of the Fermi surface. Then you match these two things, and you get exactly Ledinger's theorem. And it's completely a non-perturbative proof of Ledinger's theorem. right? So there's something you get out of this point of view. But there's just one thing. There's many other things you get. You can ask about the response to electric fields. You can ask about quantum oscillations. All kinds of things follow still within Fermi liquid theory. Now, of course, the reason to do all this by separating out some properties of the Fermi liquid as kinematic and some as dynamical, the dream is that when we talk about non-Fermi liquids, we can ask the same kinds of questions and see if we can answer them without solving the hard problem of the dynamics of the non-Fermi liquid. And we don't know, we've been trying for a few years. Maybe we'll make progress. Let's stop there.
Is this proof of the Lorentz theorem to require all generators of the one?
No, we only require particular generators, right?
So it means that even say I X can bring back individual antennas are not observed